Hey guys, welcome back to my channel. Like said yesterday, we're gonna finish off with the graphs, and today I've studied heap data structure, so we're gonna talk about that. So, what is a heap data structure? Heap is a binary tree-based data structure that satisfies the heap properties that um, so the value of each node is greater than or equal to the value of its children. So this property makes sure that the root node contains either the maximum or minimum value, depending on the type of the heap. And there's two types of heap, min heap and max heap. And the value decreases or increases as you move down the tree. Um, so I'll give you an example. So this would be the max heap where the root node contains the maximum value. So that would be like 16. And then the children node is like 5, 4, and then it keeps on decreasing its value when you move down through the tree. And the minimum tree, min heap is the other way around. Uh, the root node contains the minimum value and the value increases as you move down the tree. And I want to talk about common heap operations. Heap operations. The most common heap operations are insert, extract, max and minimum, and heapify. So insert, because heap is like a priority queue and deals with the priority queue, and it extracts or inserts the maximum element or the minimum element. Um, It uses the insert function. It also extracts max and min. It removes the maximum or minimum element from the heap and return it. Last one is heapify. It's the part of the Heap Q module in Python, and it simply converts an arbitrary binary tree into a heap. So this is already configured in Python. So if you know this heapify function, you can apply it, and then you will have your heap data structure. So that's what's pretty nice about this heap. And it's commonly used to implement priority queues, like I just said, where elements are retrieved based on their priority, so maximum or minimum. Uh, Now that we know the... Oh, I didn't even share my screen. I'll share my screen now. Yeah, this is like the basic functions to play with in Heap. So there's a Heap Q module, and we import everything. Heap does not give you a heap data structure. You just use a normal list, and Heap Q provides you with methods that can be used on this list to perform heap operations. And Heap Q, from Heap Q, you usually import the minimum elements operation, so not the maximum ones. And you initialize the heap first with the empty list, and then you add to heap using push. So it's just like a queue, right? But instead you have a heap push. So heap and one, heap and two, heap three. So now you will have heap. Now for the heap, you will have 1, 2, 3. Yeah. And you check the minimum element. In this case, that will be 1. So if you print out this heap 0, it will print out 1. You can also pop the minimum element by using heap pop. You can get the size, the length of the heap by using length. That's all the same as an array. Um, and this is how you convert, like I just said, heapify. And then when you print out nums, you can see that it's heapified. And now you can use a heap push and heap pop operation on this nums because it's already heapified. You obviously cannot use heap push and heap pop when it's normal array. Now let's try a real example. And finally, we're having an easy level example called last stone weight. So like all questions are, the logic behind is pretty simple. Um, given that there's a group of stones with, so let's say that stones are with values, just like nodes. Uh, on each turn, we choose the heaviest two stones and smash them together. And suppose that those max, so obviously we're going to turn this group of nodes, so array into heap, and then we're going to use the max element function to get the heaviest two stones, and then we're going to compare them. And if this y is bigger than x, we deduct x from y and then put back into the group. If it's the same, then we remove both. And we do this until there's no stones left, or we return the weight of the last remaining stone. Okay, so that was the logic behind it. Let's try to solve it now using the heapify function. We're going to put all the stones into a max heap. And then we just simulate the process until there are 1 or 0 stones remaining. We pop the 2 max elements and then apply the rules in the problem description. So stones is equal to minus stone for stone in stones. A simple list comprehension. We are doing the negative conversion here because Python's Heap Q module only provides a min heap. So because we did put the minus negative here, it's now doing the all stored weights are converted to negative values to simulate max heap. So this is simulating the max heap. Now we have to heapify this, and we do that using heapify function like we did just now. So we use the Heap Q module, heapify stones. So we turn the array into a heap in linear time. Now, while we use the main loop, so the loop continues until there is at most 1 stone left, and it repeatedly removes the 2 largest stones by popping the smallest negative values, compare them, and if they are not equal, the difference is pushed back into our group. So while length of stones is more than 1, we define the first, which is absolute of heap q heap pop stones. First and second stones that we take out of the group, heap q heap pop stones. And here, if first is not equal to second, then we have to deduct the second from the first stone, right? So that would be heap q dot heap push stones absolute first and minus second. Then we return minus stones 0. So what was 0 again? That was the minimum element. So the last remaining stones. If stones Q is not empty, else 0. If there are no stones left, we return 0. Uh, so we pop the smallest negative stones, negative values, and we are repeatedly doing that while in this while loop. Uh, we're repeatedly removing the two largest stones. We compare them here, and then if they're not equal, the difference is pushed back onto the heap. Okay, so let's see if this works. Heap Q dot stones minus absolute first minus second. Yeah, so that was it. Let's just comment here that the difference is pushed back into the heap repeatedly, taking out the maximum. We use the negative on the Heap Q module to simulate the maximum heap. All right, guys, that was it for today. We just introduced what a heap was. We introduced the core elements of the heap function, and we tried the most popular application of heap, which is determining the maximum element and taking it out. And we did some heapify. And yeah, that was about it for today. We're going to go into more complex stuff from tomorrow. But I think this sets the solid foundation for this heap. Thank you guys all for watching, and I'll see you guys tomorrow.